Last lecture of the year. I know some of you are really probably crying inside with no more chemistry, but let's get this over with. Acids and bases, so we've learned just general characteristics and how to use pH to tell what is an acid and what is a base. A lot of times what we really want to understand in the real world though is how those two things go together, and that's called a neutralization reaction. We also will call it a titration reaction. That's where we control it a little bit more. So just general understandings, what a neutralization reaction really is. If we go look at what an acid, what makes an acid acidic, it's those hydrogen ions. And if we have a lot of these, that's bad. I mean, that makes something dangerous. It's what causes us to feel the fatigue with lactic acid. It's what causes us to have indigestion in our stomachs. A lot of H's is bad. Likewise, if we have a lot of a base present, that can be bad too. I mean, bases can do very, very bad things to our skin and our tissues. And when we think about the word neutralize or a neutralization, I mean, if I always say if there's a guy in the halls who shouldn't be, and I take him out as the teacher, and I protect you guys, I neutralize that threat, and I don't make it so scary anymore. And that's what acids and bases do when they come together. So if you guys look, we know that this is usually going to be a double replacement reaction. And that hydrogen is actually going to go with this hydroxide and it's going to make water. So you can kind of start to use your imagination and understand, we call this a neutralization reaction because we're neutralizing these two things. They're coming together to make water. Okay, so that's one of the things. An acid and a base will always make water. And then this will always be different for different things, but then the other two ions will come together and make some type of ionic compound, and usually we can call those ionic compounds some type of salt. So it's pretty crazy in that acids are dangerous by themselves and bases are dangerous by themselves, but when they come together, they just make salt water, and that's really, really important. That's why we keep baking soda in our fume hood, and I'll show you an example of that in a second here, but an acid and a base will neutralize each other, and that's why we call it a neutralization reaction, making water and salt. Okay, so an acid and a base will always make water and a salt. So going back to my example here, when we're talking about these, if we spill acid in the fume hood, if Mr. McMahon or I are making a solution and we spill it, what we actually usually sprinkle on it, and you'll see these sitting around lab, is baking soda. And that's because baking soda is a base. What'll happen is we'll put that baking soda on, there'll be a bunch of fizzing because there's some hydrogen bubbles being released, and it'll neutralize it, and then we can just wipe it down and it's not a big deal. But we'll take a base to neutralize that acid, okay? So a little problem here, this will be like one on your homework and one on your quiz, but what if we spill 5 moles of acid? What do we need to do to neutralize that? Well, pretty simply, if we spilled 5 moles of acid, in order for us to honor this hydrogen and hydroxide relationship, I would also need 5 moles of base to completely neutralize it. So a few of the problems are very, very basic like that. There is one that's a little bit different though, and remember, this chapter still builds off stoichiometry. So another example problem here is, let's say that a student spills 3.5 moles of sodium hydroxide. How many moles of sulfuric acid would completely neutralize the base? So a lot of kids jump in and say, boom, if I spill 3.5 moles of base, I need 3.5 moles of acid. But there's one little catch we have to make sure we pay attention to, and that's that sulfuric acid is special. So in order to kind of illustrate this, we start just like in stoichiometry with the blank equation, which I have here. I spilled sodium hydroxide, I have sulfuric acid to neutralize it, and the main thing is when we go do that double replacement, the outside goes with the outside, the inside goes with the inside, you guys can see here's my water, and then my salt would be sodium sulfate. It's not balanced. When I go balance this out, I can see I have 2 sodiums, so I need to start with 2 sodiums. So there's my nice balanced equation, and I can see here that because there's 2 hydrogens, we call this a diprotic acid, I only need 1 mole of sulfuric acid to keep up with 2 moles of sodium hydroxide. So it is true that I am going to need 3.5 moles of acid, but if I go through and do my dimensional analysis, I start with 3.5 moles of this, and I can see from my mole ratio that I only need half as much. So there's my little dimensional analysis step. Moles of sodium hydroxide cancels moles of sodium hydroxide, and I actually only need half as much because for every 1 mole of sulfuric acid, I get 2 acidic particles out of that. It won't always be that catchy, but sometimes, guys, you just have to remember to go do the reaction. Okay, the reaction will always help you. Now, getting into a titration reaction, it is a neutralization problem that we do, but it's where we control what we're using to figure out an unknown. We're trying to figure out what we don't know about an acid, or we're trying to figure out what we don't know about a base. So this is our little equation you'll use. I think Mr. McMahon teaches it a touch different, but he'll use the letter L instead of V. But you can see on the left side of the equation, it's N times MAVA equals N times MBVB. And what we're really doing here is saying moles of this has to be equal to moles of this. If I spill 10 moles of this, I need it to be neutralized by 10 moles of this. The little A's right here stand for the acid we're talking about. The little B's right here stand for the base we're talking about. So MA stands for the molarity of the acid. MB stands for the molarity of the base. That's what our last lesson was about in stoichiometry. And obviously, if I spill a gallon of acid versus a drop of acid, the volume is a big deal. So VA is the volume of the acid. VB is the volume of the base. And everyone, Mr. McMahon teaches this a touch differently, but when we're thinking about the number of moles, this little n is important. And that example we just did with sulfuric acid shows us why. For every mole of sulfuric acid I have, I produce 2 moles of that hydrogen ion. So I always teach that this little n right here stands for the number of H's that you have. So if we're talking about HCl, n is 1. If we're talking about H2SO4, there's 2 of those. So that's where that coefficient will come into play. Likewise, over here on our base, this will stand for the number of hydroxides, because that's what bases produce in solution. So if it's sodium hydroxide, N is 1. If it's calcium hydroxide with parentheses 2, that N value would be 2 there. So this is a fairly straightforward equation to use, but I always call this my neutralization equation. So let's do one example problem, and you guys are going to see it's really a plug and chug type of problem. A student in a chemistry lab carelessly knocks over a flask that had 25 milliliters of 1.50 molar hydrochloric acid. Nearby there is a container of 0.75 molar sodium hydroxide, and I want to know how much of the base should I pour on it, or mix with it if it's a powder, whatever the case might be, to completely neutralize the acid. So I can tell that this is an acid and a base problem, so I'm going to use my neutralization equation, and I'd always start with your blank equation. Then we're literally just going to go plug in what we know. I can see that since it's hydrochloric acid, N is 1. Some of your practice problems will not have a 1 because they have 2 H's. The molarity of my acid is 1.50 molar. I spilled 25 milliliters of my acid. Since it's sodium hydroxide, my N value is 1. The base I have is 0.75, and I don't know my volume. That's what the question's asking me. So I'm going to leave this as VB. Then you're just going to algebraically get volume of base by itself, and what we'll see is that it would take 50 milliliters of base to neutralize that acid, and that makes sense. I need way more base. I have 50 milliliters of my base because it's not as concentrated as my acid. Since my acid's 1.5 and this is 0.75, it's going to take a lot more of this to keep up and neutralize to make that salt water. Start with your blank equation. Carefully plug in what you're looking for, isolate what the problem's saying, and then rock and roll from there. Pay attention to your units and be a good problem solver. Go get after that last homework assignment of the year.